Welcome to the Mechatronics Revolution Fundamentals and Core Concepts. In this lesson, we'll talk about amplifier circuits. The learning objectives of this lesson are to first explain the use of operational amplifiers or op-amps in mechatronic design, identify some common op-amp configurations and explain how they work. We'll design an amplifier circuit for an example application. And then finally, we'll discuss at the end the need for something called a common ground in a mechatronic device. Typically in mechatronic design, we have signals that we might need to amplify. For instance, sensors. Typical sensor output we may need to amplify in order to read it appropriately on the microcontroller. When amplifying voltage signals, we typically amplify them in a linear way where we have a certain gain that's multiplied times the voltage, V in, to produce an output amplified voltage, V out. An example where you might need to do this is a particular sensor, for instance, called a thermocouple. A thermocouple is a temperature measurement device that outputs very low voltage signals that need to be amplified to a proper range in order to be read easily by a microcontroller. A common circuit element that's used to amplify voltage signals is called an op-amp, or an operational amplifier. Op-amps are built from transistors, diodes, resistors, and capacitors. And they're used for, first and foremost, for signal amplification, but as we'll show in a few minutes, are also used for other purposes. The two inputs to an op-amp are called the inverting input and the non-inverting input, and we'll see how those inputs are used in amplification circuits. The output to an op-amp is shown here, and we also have two other inputs to an op-amp that supply the op-amp with power. So those are called the rail inputs, or the supply inputs, and they typically require voltages at the plus or minus 15, so a positive supply of 15 volts and a negative supply at negative 15 volts. And those rail voltages vary in magnitude depending on the model of op-amp that you use. The first way we can use an op-amp is in something called open loop operation. In open loop operation, our inputs, we directly provide inputs to the inverting input and the non-inverting input. The output voltage, VO, is then computed as the difference between the non-inverting input and the inverting input multiplied times some scalar gain, some value KOL, or K open loop. For op-amps, K open loop is usually a very large number, like 10,000 or 100,000. So this gain is extremely high. Now the op-amp can only output the maximum voltage of what we call a saturation voltage, VSAT, or negative of a saturation voltage. So even though K open loop is very large, what happens is even with small differences between V plus and V minus, our outputs saturate to either positive VSAT or negative VSAT. And you can see that in the diagram on the right, showing that as the difference between those inverting and non-inverting input voltages, as the difference becomes even a very small difference, the result is either the positive V saturation or negative V saturation. So typically with an open loop operation of an op-amp, we only get two voltages output, usually plus VSAT or minus VSAT, depending on which voltage, V plus or V minus, is larger. When we operate an op-amp in this configuration, that's usually called a voltage comparator. A closed loop operation of an op-amp looks a little bit different. So in closed loop operation, we will use what's called feedback to drive the op-amp. Let's look at first a non-inverting op-amp circuit. A non-inverting op-amp circuit is used to amplify a voltage signal, and the amplifier gain that relates the output voltage VO to the input voltage VI is a relationship, it depends on the relationship between the two resistors that we use in this feedback circuit, R1 and R2. So the amplifier gain is shown on the right-hand side of this slide and is 1 plus R2 over R1. By sizing R2 and R1 appropriately, we can set that amplifier gain to whatever value we want within certain bounds. Now, since resistors only come in discrete resistance values, if we want to set a precise gain, we usually need to make either R1 or R2 or both, a potentiometer so that we can tune them to the value that we want. And we'll be using non-inverting op-amp circuits quite a bit as we go throughout this course. A similar type of amplifier circuit is called an inverting op-amp circuit. So this inverting op-amp circuit, or inverting amplifier, is used to amplify a voltage signal and also invert it. And the gain, so the gain is shown here on the right-hand side of this slide, is again driven by the resistance values R2 and R1, except now the output voltage is negative of the gain times the input, and so it inverts the voltage from positive to negative or vice versa. Inverting op-amps are sometimes used in what's called a current to voltage amplifier, where we convert a current output from a sensor to a voltage output, which are easily read by a microcontroller analog to digital converter. Let's look at an example where we want to design an amplifier circuit to take an input voltage and put it in a different range of output voltage. So for this example, we want to take an input voltage VI and produce an output voltage that's a gain K times VI. And we want that gain K to be tunable from a value of 1 to 10. So we want to think about what circuit components are needed, and then we want to find an expression for this gain in terms of the circuit component values that we use. To solve this problem, we'll use a non-inverting op-amp circuit. We'll amplify the voltage using this non-inverting op-amp. Because we want a variable gain, we want K to be able to be varied between 1 and 10, we'll make one or both of the resistors a potentiometer. And you can see that in this diagram we've chosen to select R2 as a potentiometer because it has that arrow underneath the resistor. Let's look at what the actual gain of this amplifier is going to be. So looking back at the non-inverting op-amp equation, we have V out is equal to 1 plus R2 over R1 times V in. So the gain K is 1 plus R2 over R1. Now we need to figure out what we want R2 and R1 to be. We know the range we want for K, but we have two resistance values to choose, so we'll go ahead and select R1 to be 1 kilo ohm. And now we can finally solve for what R2 has to be. So if R1 is 1,000 ohms, then that means that R2 has to be, we can select a potentiometer that can be tuned between 0 and 9 kilo ohms, and that will produce a gain K that varies between 1 and 10. Let's look at a common type of op-amp, the LM741, which is commonly used in mechatronic devices. The LM741 has rail voltage inputs that must be supplied at positive 15 volts and negative 15 volts. It's important to understand also that the input terminals to an op-amp, such as this LM741, are very high impedance, meaning that the resistance of these input terminals is in the mega ohm range. So almost no current flows into the input terminals. So these types of devices will not draw a lot of current from the inputs themselves. You can see a pinout diagram of the LM741 here, and these are fairly cheap types of circuit components that usually cost less than $1 or so. Oftentimes it can be hard to generate large negative rail or supply voltages in a circuit. For instance, the negative 15 volts that we have to apply is a rail input to the LM741. As a result, you can buy single supply op-amps that eliminate the need for a negative rail voltage, and instead we can hook the negative rail voltage to our ground, our voltage ground. And here's an example of a single supply op-amp that's made by Texas Instruments. Before wrapping up, I want to talk briefly about grounding. In mechatronic devices, it's common that we have several different circuit components and circuit boards connected together. It's important that we ground each of these circuit components to the same common ground. If they're grounded to different items on the device, maybe different components, that can set up what's called a ground loop, which can cause serious problems, for instance, noise or bias in our circuits, and cause problems in the operation of our device. And this happens when these different circuit elements are grounded to different ground points at different electrical potentials. We can get what's called a feedback current. In order to avoid this, we want to connect all of our circuit components to a single common ground that eliminates our feedback currents and usually will solve those types of problems. To summarize what we've learned in this lesson, first, op-amp circuits are used for a variety of purposes in mechatronic design, and they're usually used to amplify signals or possibly compare voltage levels between two inputs. Voltage amplifiers can be built using op-amps combined with resistors and potentiometers to build inverting or non-inverting amplifiers. Finally, it's critical when we design and implement a mechatronic device to create a common ground, and that avoids feedback currents and makes our outputs and performance a lot more predictable.